In this video, I would like to talk about the continuity test. I have a definition for continuity at an interior point here on the board. In a previous lesson, you know that there's a definition for continuity at a left endpoint and a right endpoint. But for right now, I just want to consider continuity at an interior point. If c is a real number, f of x is continuous at c if the limit as x approaches c matches the function value, f of c. When we were talking about limits, we saw three pictures. In each picture, I have a function whose limit as x approaches c is the real number L. In this last picture I'm going to draw, we have the case where the limit and the function value match. That makes us happy. That's a continuous function. Better said, this function is continuous at the real number c. There is no function value here, so my function is not continuous there. There is a function value here, and the limit exists there, but they're different, so my function is not continuous there. So these were all examples of, these three were all examples where the limit as x approaches c of the graphed function f of x was L. All right, the continuity test is a way to check and see if a function is continuous at a particular real number. But what it really is a slowed down way of thinking about the definition of continuity. In the continuity test, I just asked myself three questions. So let me write it down and then we'll go through the question. A function f of x is continuous at c if and only if it meets the following requirements. One, the function value has to exist. Well, for this equation to be true, I need a real number on both sides. The limit only exists if this is a real number. So that's what this is checking for. Making sure that when I plug f of c in, I get out a real number. Two, the limit must exist. So number one is making sure I get a real number on the right-hand side. Number two is making sure I get a real number on the left-hand side. And then the third and final part of the continuity test is that those two values are the same. This gives us a way of thinking about continuity in a way that we can easily test it. It also gives me a way of looking at a function and telling you why it's not continuous, because I could just tell you which part of this it broke. If the function value is not defined, that's a good reason to state if a function is discontinuous. If the limit doesn't exist, or if the two things are different. So let's go through different types of discontinuities. I could have left the top two pictures I had drawn here, but I'm going to go on and redraw them. These functions are not continuous at c. This one's not continuous at c because I violate this first rule. F of c is not defined. This function's not continuous at c because these two things don't match. I have a function value, but it's in the wrong spot. Now, both of these are what we call removable discontinuities. Because I could just define the function in this top picture to be defined right at that point, patching the discontinuity, literally removing the fact that it wasn't continuous. In this function, I have to pick this piece up and kind of put it where it should go to make it continuous, but I could remove the discontinuity. I actually prefer the term patchable discontinuity because that's really what I'm doing. These functions had holes in them. To make it a continuous function, I think about patching the hole. The technical term, removable discontinuity, and we could think of it like this. If a function had a finite number of holes in it, we could go around and we could patch all of the holes. Those would all be removable discontinuities. All right. Another discontinuity at C would be a function that looks like this. In this, the limit fails to exist. When that happens, or at least in this particular way where I have a left limit that does exist and a right limit that does exist, we call this a jump discontinuity. All right, a couple more pictures. Oop, ignore that. Someone forgot to erase my board. That would be me. All right. More functions that are not continuous at C. If I have an asymptote at C, then very clearly the limit doesn't exist. It grows without bound or falls without bound. I don't get a real number, but also the function value doesn't exist. So it fails all three parts of my continuity test, and I call this an infinite discontinuity. And even if I had a function that on one side was going up and the other side was going down, or all going down, I would still just call it an infinite discontinuity, even if it was tending towards minus infinity. All right, and then one more. I could have a function like sine of 1 over x. And we saw that function in one of the previous videos and learned that it just oscillates so much that the limit doesn't exist. And this would be called an oscillating discontinuity. All right, so we have removable discontinuities, jump discontinuities, infinite discontinuities, and oscillating discontinuities. And for all of them, I could actually go back to the continuity test and give one of the three parts as the reason why it wasn't continuous. This function, not defined at x equals 0. And that's why it's not continuous at 0. All right, I'm going to post another video here in just a moment that uses a continuity test in an example, but that's it for now.